Hi, my name is Nathan Glover, and today I'm going to give my third progress report and conclude the first half of my project. In my previous videos, I discussed the angle mapping problem and some of the methods I would try to implement. I was also working on HSV color detection instead of RGB. I worked a convex hull and rendering method around the contour points and tried to achieve all of this in real time. Previously, to do my object detection, I was using an RGB range as my delimiter. I recently tried out HSV and was blown away by its results over RGB, so I decided I'd go about learning why HSV was so much better for object detection. So let's take a look at an example. Say we wanted to detect a typical stop sign on the side of the road. The first thing a lot of people might do is use an RGB red value as a search parameter. Obviously, the color red on the sign isn't going to be the exact value we're looking for, and when I say red I mean the RGB equivalent, or 25500. So we need to use a range. So say then we take a range of 130 to 255 as our R value in RGB, but we still don't have any luck. The issue is that our color red is actually made up of green and blue components as well. However, when we try to scope the range to include red and green, we end up with false positives. So we need to find an alternative. You can see the issue of false positives in the image on the right, where we've used a color picker to inspect the color of the red stop sign. Our R, or red value, is 218, our green is 34, and our blue is 36. So at this point I feel like I need to explain how RGB and HSV work respectively. We'll start with RGB. RGB is defined by listing how much red, green, and blue is contained in a single value, or pixel, in that image. It uses an additive method where the more of each color that is added, the brighter it becomes. It's very hard just by looking to arbitrarily decide how much of each primary color is needed to construct a desired filter or color. HSV, on the other hand, uses three parameters to describe the color: hue, saturation, and value. The hue, typically between 0 and 360, but in the case of OpenCV it's 0 and 179, represents one of the core colors along the spectrum. Saturation represents how pure we want the result looking, or if we would like it to be washed out. And the value, also described as the brightness, represents the color between the ranges of white and black. I've set up the images on the right to sort of show you what kind of colors we'll be dealing with if we were trying to detect red. So with a H value of 0, we have a very red sort of area we're looking at, and our SV values are set to 150 respectively. If I bump the hue up to 10, I immediately see that I'm working in a range more like an orange. And then if I scale the 150 SV values up to 255, we slowly get more and more into that right-hand corner where we get a much more pure, solid red value. And now I'd like to talk about the real meat in this discussion, which is the angle mapping. And I'd like to break down the process before I speak about each part. The mapping process follows these simple steps. First, we generate a HSV matrix, compute the HSV thresholds, find the contours and the moments, and finally the mass centers. Finally, we draw the contours, compute the final angle, and draw this onto the image. You can see an example of this output image on the right. This is taken directly from the live video stream. So to start with, we need to declare our variables. I decided that I'd declare them prior to any code execution to make things simpler when it came to reading the code. Color 1 and color 2 store the colors that will be used to outline the two detected objects. The rest of these primitive variables are all defined in my project blog. In the following line, I convert the image frame taken from the webcam from BGR to HSV. BGR is the reverse input of RGB, and it's how we store our RGB values in a scalar data type. So let's look at an example where RGB of 25500 would typically be stored as 00255. This is something very important to remember, and I discussed it early on in my project blog, but OpenCV stores RGB channels in reverse order, so RGB is actually BGR. BGR of 00255 is stored as 00255, which makes things more simple when you're writing your code. Next, I compute and generate two threshold maps, one for each of the two colors, using the CVInRange function. This method takes four arguments: an input image, a scalar color 1 that represents the minimum threshold value, scalar color 2, which represents the maximum threshold value, and a pointer to a location where we store the output image. Next, we run our find contours function using some typical arguments that we've already discussed in a previous post. We store the two different contour maps in the variables contour1 and contour2. Finally, we call the moments function to find the largest mass of a particular colored object in that image frame. You can think of moments as little pockets of information that we are very interested in. Whenever we find a space in that image that represents one of our two colors, we add that to a moment. If enough moments are clustered together, they'll represent a much larger object. And due to the way that we only store the largest of a found moment cluster, means that we will end up with two objects in our scene when we're searching for two different colors. The final step, and arguably the most important step, is to draw the contours onto the output image, and then using each of these two large objects, based on their center point, we compute an angle using the arctan function. The aforementioned code and process allows us to get an image similar to the one displayed on the right. It runs in real time and simply finds two of the largest objects, which in the case of this picture are red and blue. These objects have their relative angle between them computed using the arctan function, and then displayed. Here's an example of it working in real time. Hey, so I'd like to quickly demonstrate in real time the angle tracking of the sensors. So eventually this sensor here will have an accelerometer within it that'll allow me to sort of draw out where gravity is coming from. So instead of having this straight line across here, but for now this is what I've got. And then I've got the blue sensor, which is used to, I guess, find and transform the angle in relation to the yellow sensor. So this all happens in near real time pretty quickly. It also doesn't mess up very often. And I do something really interesting with the center point of mass for each of these objects. So you'll find that if you cut off half of the object, the center point of mass is actually shifting. So this is my workaround for ensuring that I'm comparing a point on the object that is always going to be very similar. So another idea I had was to take the center point of this white line, but this center of mass method using moments has actually worked a lot better. So that's a quick demonstration of how this will work on a horizontal frame. This doesn't work as well for the top-down method. So again, I mean, it can be used and it will be implemented in a fashion similar to this. However, right now, it's not fully accurate, so I'm still working on a method for that. As I briefly mentioned in the video prior, the next step I'd like to take on my project is to find a way to map the hand from a top-down view. This means computing angles between fingertips and also finding, detecting the piriform bone on the hand and using that as my center point when detecting and computing angles. I'd like to conclude by saying thank you very much for following my progress, and I hope my blog and my videos have been very helpful and have taught you some things. If there's anything you'd like to ask me, or if you have any information you think could help me, I'd love to hear from you. You can contact me at nathan@glovers.id.au or on my student email at nathan.glovers@student.curtin.edu.au. Thank you very much for your time.